Okay, this is section 4.2, part 1, compound events. What's the probability of something happening and something happening after that? And these are and problems. When you're presented with an and problem, many times the word and is right in the problem, but many times it's just implied. And problem, you're going to multiply the probability. But before we even start that, let's think about events being dependent or independent. Events are said to be dependent if the occurrence or non-occurrence of the first thing somehow affects the probability of the second thing happening. Not that it caused it, but just affects the probability, increases it or maybe decreases it. Number one, a mosquito lands on your arm, you get bit. Well, yeah, the fact that the mosquito landed on your arm would definitely increase the probability that you're going to get bit as opposed to a mosquito not landing on your arm. A green ball is drawn from a box with 5 marbles and placed next to the box. A red ball is drawn next. Well, if you draw the green one out, you put it off to the side. Well, guess what? There's only 4 balls left, so the probability of getting a red ball is diminished because you've taken one of the balls out of the bag or the box in this case. A man visits New York on vacation. He visits Central Park. Did the occurrence of him visiting New York change the probability or affect the probability? Yeah, well, New York. Well, the Central Park is located in New York. If a man visited, let's say Cleveland, well, it's not going to affect the probability. But he's in New York, so doesn't mean he has to go to Central Park, but it sure affects the odds. It's going to improve it because he's right there in the city where Central Park is located. You cook your chicken improperly, you get salmonella poisoning. Well, obviously, the fact that you cooked it improperly affects the odds of you getting salmonella. The fact that it increases it as opposed to you cooking it properly, right? Dependent events. Number 5. All right. So the first thing I noticed is that you don't have a raw count here, given percentages. Types of problems like this, these are actually dependent. All right. You've got a Democrat, you pick a Democrat, you put them off to the side. Well, guess what? There's less Democrats to choose from. So theoretically, these problems are dependent. But since you're not giving a raw count, you're given a percentage. It'd be incorrect to say, well, the probability of a Democrat is 0.39 first time out and then 0.38. Subtracting a percentage point and subtracting an individual is not the same. 1% does not equal 1 unless for some reason there's 100 people. These are actually easier problems for you. Even though they are theoretically dependent, you treat them as independent. In other words, you use that 0.39 for the probability of picking the first Democrat, and which means we multiply 0.39 probability of picking a second Democrat. If you're picking a third, it'd be times 0.39 again. Theoretically, these problems where given percentages are dependent, but we treat them as independent. The very thing follows in number 6. You're not given a raw count. You're just given a percentage. The probability of getting something that's acceptable is 70%. All right. Now, you're just not going to say, well, it's 0.70, then 0.69. No. Subtracting a percent and subtracting one individual aren't the same. So you actually catch a break here. When you're given problems with percentages, even though they are dependent events, you treat them as independent and you use the same percentage over and over again. Number 7, slightly similar. The thing is now you're doing this with replacement. All right, so what replacement means, you're starting all over again. The probability of getting a good light bulb, if there's 78 and 9 are defective, well, apparently, or not apparently, but obviously 69 must be good ones. That's what he's not telling you. If he tells you how many defective, it's not that difficult to figure out how many of them are good if you know there are 78 all told. There's 69 that are good light bulbs. All right, we pick that good one out, then we put it right back in. So the probability of getting another good one is the same thing, 69 out of 78. We pull that one out, we put it back in. You're starting all over again. Nothing changes. So with replacement, you're using the same probability, 69 out of 78. 78 good total light bulbs, 9 defective, and 60. I'm saying 68, but it's actually 69. 78 subtract 9 is 69. 69 out of 78. 3 different times. Now, if it were without replacement, Then it'd be 69 out of 78 times 68 out of 77 times 67 out of 76. You'd have to subtract one from the numerator and one from the denominator. But with replacement, you're doing the same thing over and over again. Number 8 is just like number 6 and number 5. You're given a percentage of the adults who have health insurance. You're not giving a raw count. Here again, this is theoretically dependent, but with percentages, you keep it the same 4 different times. The probability doesn't change. So problems with percentages actually are to your advantage because you use that same 0.79 4 times. Please do not subtract 1 from 79 to get 78 and then 77 and 76. 1% in one individual is not one and the same unless for some reason he told you 100. That's not going to happen. So you get your break with those. All right, find a probability that 3 randomly selected people all have the same birthday. Well, here's the deal. The first person can have any birthday they wish. All right, it's the second and the third that have to match up with the first person. At first person can have any one of the 365 out of 365 for their birthday any day. All right, so this is nothing more than a whole number 1. Now that second, let's say the person's birthday is September 19th. The second person has to have that same birthday, September 19th. All right, there's only one day out of the year that's September 19th. There's one chance in 365. The third person also has to have that same exact birthday, September 19th. Well, there's only one day that is September 19th. So it's 1 over 365 times 1 over 365 times 365 over 365, because the first person, they're not limited. They could have any birthday. It's the second and the third person that have to match up. Now, what happens is you get an answer in your calculator of 7.51 E negative 6. And E negative 6 means take the decimal point here between the 7 and the 5, move it 6 places to the left. That's why you've got 5 zeros followed by a 7, 5, 1. Negative 6 implies taking the decimal point, moving it 6 places but to the left. That's what the negative means. You dealt 2 cards successively without replacement from a shuffled deck. Now, if he didn't say without replacement, you would assume without replacement. When they replace things, they have to tell you. Here, he's just being a nice guy and say, oh, by the way, I'm not replacing. He didn't have to say that. All right, find a probability that both cards are black. Well, half the deck is black, the clubs and the spades. There are 26 out of 52 cards in a deck that are black. If I take a black card out, guess what? I've only got now 25 black cards, and there's only a total of 51. If I did it a third time, it'd be times 24 over 50, and then times 23 over 49, and so forth. All right, definitely dependent events. Number 11 is kind of similar to number 9. You got 4 randomly selected people. Find that the probability of having different birthdays. The fourth person has to have a different birthday than the third has to have a different birthday than the second, and the second has to have a different birthday than the first. The first person can have any birthday they wish. The second person has to have a different birthday. Let's say that first person's birthday is once again September 19th. The second person has to have a birthday that's not September 19th. How many days in a year are not September 19th? 364 days out of a 365 total. The third person, let's say the second person now, his birthday is July 5th. The third person can't have September 19th, nor can they have July 5th as a birthday. They're limited to 363 days that aren't September 19th nor July 5th. Let's say this third person has a birthday of January 8th. The fourth person can't have September 19th. They can't have July the 5th, and they can't have January the 8th. There's 3 days that they can't have because we want all 4 people to have different birthdays. Well, how many different days are there that aren't those 3 that I just mentioned? Right? Aren't September 19th or aren't July 5th or aren't January 8th. There's 362. A total of 365. And if we did it again, it'd be 361 and so forth. That's a little different. That's kind of not a trick question, but once you see it, this first person is not bound to have any birthday. They can have anything they want. This is basically, you do these, see one like this first fraction is something more than the whole number 1. Among the contestants in the competition, 49 are women, 20 are men. I think we did this in the PowerPoint. What he hasn't told you is that it's a total because, it's favorable over total. There's 49 women, 20 men. There's obviously 69 total people. How many are men? 20 out of 69. If I pull one woman out, there's only 19 women out of a total of 68 total, then 18 out of a total of 67, 17 out of 66, and then 16 out of 65. I've actually put these in parentheses. When you put this into your calculator, the calculator is smart enough. It knows order of operations. There's no need when you do this with your calculator to use parentheses. The calculator will follow. It'll multiply or divide before it does anything else. Many times you're given these problems, these and problems, or even the or problems for that matter, you're given a table. All right. He wants the probability, number 13 here, of randomly selecting a person, 2 people out of 948 people, and find a probability that these 2 people are heavy smokers. Well, I can see here that 81 out of the 948 are heavy smokers. If I pull that person out, then now there's only 80 heavy smokers out of a total of 947. See, this is an and situation. Heavy smoker and another heavy smoker. And if I did it again, it'd be 79 out of 946, right? And problems. Here's a case where the and is not, doesn't say the word and, but it's assumed. I want a heavy smoker and I want another heavy smoker and I want a third, that was the problem, the third one. But 2 different people. Let's see, number 14. What do we got here? Smoking habits. 2 different people are selected out of 884. Find a probability that they're both women. Well, first time out, there's 506 out of 884 that are women. Take that woman out, there's only 505 over 883. Now, of course, if I was with replacement, this 506 over 884 would remain constant. You can't assume replacement. When there's replacement, he tells you. If he doesn't say anything, you don't assume replacement. So there's always going to be one less. Did it a third time, it'd be 504 over 882 and so on and so forth. All right, let's see, that's 14. And a sample of 4 different calculators randomly selected from a group containing 46 that are defective, 26 that had no defects. Well, the missing part here is you need the total. It's favorable over total. Take 46 and 26, you get 72 total calculators. We want the probability that we pick 4 of them, they all are defective. Well, he tells me that 46 are defective first time out. So it's 46 over a total of 72. And the next one is defective. Multiply, it's 45 out of 71, and then 44 out of 70, then finally 43 out of 69. If you did it again, it'd be 42 over 68 and so forth. Once again, putting these into your calculator, you don't need to put the parentheses. It wouldn't hurt. It's just not necessary. The calculator will do the order of operations. All right, so that's 4.2, part 1.